brother has sent it over like this here actual word that one no they so you like it. So it's gonna be like hours. Explain.
Yeah, talk about what I say for that section. Sorry. Yeah, I'll talk about it. And then, you know, if you have a question at that time, just that way everybody hears it. Yeah. All right, so let's go ahead and begin today. So today's class is all about Lab 4. And to really understand Lab 4, you have to understand two's complement. So I'm going to go over how the overall circuit is supposed to work. But before I do, I want to just review, two's complement from last time. Remember, there's 3 forms of sign binary numbers. There's sign magnitude, 1's complement, and then 2's complement. And 2's complement is also called radix complement, so that's the RC. So, but of the 3, 2's complement is the one to focus on. Okay, that's the most important one for this class. It's also for any other digital class you take dealing with sign binary numbers. It's most likely going to be the most important one. And then also, I put on each table enough copies of my midterm policy along with the topics for the midterm. That's the same information that's on Canvas. Okay, but I thought I'd make a hard copy just so I would be sure everybody got one. So after I'm done with the lecture portion, I'll go over that and take any questions you have about it. Okay, so first of all, like I said, just let's do a review of what we talked about last time with two's complement. So first of all, when you have a two's complement sign binary number, how can you identify if it's positive? Right, exactly. The most significant bit, the MSB. And remember, what bit is that? The most significant bit, where is it? All the way to the left. That's your sign bit. Right, and it's a 0 when it's a positive sign binary number. Now, how do you find the magnitude of a two's complement positive sign binary number? Like, you know it's positive now. How do you get the number, the magnitude? It's positive. What is it?
You just
Okay, how do you do it? You add what?
like
What is it like previously? Like, what have you done previously that it's the same thing? So when you get the magnitude, doesn't it? Well, I'm just talking about the positive number itself, like not talking about adding them yet. How about if we have an unsigned binary number? How do you find the magnitude? Right, if I have an unsigned binary number, how do you find the magnitude of this? You all know this. You just don't want to tell me?
You add both bits. Let's see what place the bits are.
Okay, so that's what you're referring to again. Yeah, you add the bits, right? This is the 1's column, right? 2's, 4's, 8's, right? So this would be 5 in base 10. Okay, so how do you find the magnitude of a positive sign two's complement number? Same. That's what I was trying to get out of you. That to find the magnitude of a positive number on two's complement, you do the same thing as you would an unsigned, right? Yeah. So same as unsigned. Pull in T. Same as unsigned. Okay, but now if it's a negative two's complement number, how do you know? How do I check? What's 1? Yeah, the sign bit is a 1. All right, and then how do you find the magnitude of a negative two's complement number? Add what else? Okay, but I think you're missing one step. What do you do before you add them all up? Yeah, you got to flip it. Yeah, you flip the bits, then you add. Yeah, flip the bits, add 1, then do the same. So yeah, flip bits. Right. So does this sound familiar? Okay, good. All right. We also talked about validity rules, right? That anytime you do signed binary addition, you gotta make sure the result is valid. So do you remember the rules? Can you give me one of them? Somebody?
Positive plus a negative is all something valid.
Yeah, exactly. That's, if you take a positive plus a negative, always no. And again, the way you can reason it out is if you just think of a number line, like say you had a number line. And did you have a question or? Oh, okay. Let me just say this little thing and then I'll take either person. You can give me one and you can give me the other. But I just wanted to, you know, make the same comment I did last time when I talked about this, that, you know, the way you can reason that, you know, positive or negative must always be valid is that if you just think of a number line where, you know, you have some negative value on that number line and some positive value, right? You have this range from that negative number to that positive number. Well, as long as you add two numbers in between those two extremes, one negative, one positive, the result is going to be within that range. Okay, and remember, that's another way to think of when the result is valid, is that the result is within the range for that number of bits that you have. Okay, all right, so give me another one.
Positive and positive, positive.
Okay, so positive plus positive, valid, the result is positive. And I think most people don't have trouble with this, right? Because I mean, you can't add two positives, you get a negative result, right? And then do you want to say the third one?
Negative.
Yeah. So it's negative plus negative. Valid. If result is negative. Okay, and then, you know, last time we talked about how for the lab 4 design, there's an RCA that you have to modify, you know, make all full average, right? Actually, while I think of it, because this came up last class, and I'm not sure if I mentioned it in all my sections. So in case I didn't mention this before, when you bring over a file from another project, like when you bring that RCA from like project 2, right, over to project 4 for lab 4 to modify it to make it all full average, there's a little checkbox that says something to the effect of, you know, a copy version. Make sure that's checked, because if you don't check that box, when you bring over that file into the new project, you start editing, it's going to edit the file that's in the old project too. Okay, so did I mention that in class? Okay, sorry about that. Maybe some of you have found out the hard way where you did that, you saw that we changed it. So with that happening, sorry I didn't mention it earlier. And then also, you know, last time we talked about after you modify the RCA and test it, that you could also create the validity module, right? And remember I said there was 2 ways that you could design that module. Can you give me one of the ways I said? Yeah, you could do an if statement where that if statement is performing these rules. And then do you remember the second way? I mean, most people do an if statement, but you can also do something else. Yes. Yeah, you can make a truth table of the sign bit for each of the numbers you're adding, the sign bit for the result, right? That would be the input side. The output side would be call it valid, like the output here in the diagram. And then you could just put in the 8 different cases and just, you know, put what the output would be, right? Because actually, let's that here. And you have your sign bit for A, your sign bit for B. Let me just tilt this real quick. There we go. But yeah, you make a truth table. Where on the input side, you have your sign bits for the 2 numbers you're adding, right? The sign bit for the sum. Your output would be valid. And then you would put in the 8 combinations, right? But since we have 3 bits, we can have 8 combinations. And then you would just look at this and go, okay, well, when the sign bit is a 0, that's positive. So I'm adding two positives here, and I'm getting a positive out. So what would I put for valid? Assuming if it's valid, it's a 1, not valid, it's 0. Yeah, you put a 1, right? Because that's right there. Positive plus a positive, valid if positive. Next one, I'm adding two positives, the result negative. What would I put for valid here? 0. So you would just fill out the truth table, right, based on those rules, and then you could put this into a K-map, right, it'd be an 8-cell K-map. You get the reduced expression for valid. Right, and then you could just put that in Verilog, right, use another sign. And just like we did in the first two labs, we were coming up with Boolean expressions, and we put the Boolean expression into Vivado, Verilog code would just be an assigned state. So, yeah, so anyway, any questions up to this point? Let's put the camera back here. Okay, so we also did a number of examples. In fact, I did a bunch of examples on the activity last time, but let's do it just a few more here just to get your minds back into binary addition here. So like we talked about last time, when you're adding signed binary numbers manually, it's the same as when you're adding unsigned manually. What's the big difference though? In fact, it's really the only difference. Between unsigned, signed. Unsigned and signed, what's the big difference? There's a signed bit, exactly, right? This most significant bit is the signed bit, which doesn't have numerical value, right? But the way you add the bits, right? So 1 plus 0, 1, 1 plus 0, 1, 1 plus 0, 1, 1 plus 1, 0, carry the 1. Okay, so anytime you're doing signed binary addition, the first thing you got to think about is whether the result is valid. So what's our answer here? Is it valid? No, why not? Yeah, we're adding two negatives and it's positive. That's not valid. Now you can also convert these to base 10 like we did last time, and just make sure it makes sense in base 10. I mean, it's not absolutely necessary, but you could do that. See, a common error, and the reason why I write the S just so it's explicit to me that that's the sign bit, is I can't tell you how many times I'll have a person, when they see this 1 over here, they think that's the sign bit of the result. And then they think this is negative, and then they think it's valid. Okay, but what do we do with a bit to the left of the sign bit in a result? You just ignore it. Doesn't make any sense. Okay, the sign bits line up. Okay. All right, let's do the next one. This would just be 1, 1, 0, 1. What do you say, valid or not? Valid, what? Okay, you're adding a negative and positive, always valid. It doesn't matter the order, by the way. I could put, negative plus positive, always valid too. Doesn't matter what order. All right, so this is valid. And again, you could convert these to base 10, to check them, but that's not necessary. Okay, so now remember, practical digital circuits, they do subtraction by addition. Okay, instead of doing straight subtraction. And remember last time I talked about there are subtraction rules, and you could make a circuit that does direct subtraction, but that would be a whole nother piece of hardware, right? So if you can do subtraction by addition, you can use the same RCA that we came up with for addition. And that's in fact what you're going to see here in lab 4. And we talked about this diagram. Okay, but what's the big step? In order to do subtraction by addition, what's the big step that you have to do? If we want to take this number here, well, we want to take this number, subtract it from this top number. So what do we do? Yeah, you take this second number, you flip it, add 1, because you take the 2's, Right, again, this goes back to, there's two meanings to two's complement. The noun is that listing that I gave, right, that showed, you know, the two's complement binary representation of, 4-bit two's complement numbers from, +7 to -8. That's two's complement the noun. Two's complement the verb, like take the two's complement, like you ever hear someone or you read somewhere that they're taking the two's complement. They're negating that number. Right? You can take the two's complement of a positive number, you can take the two's complement of a negative number, and you're always gonna end up with the negation of whatever you took the two's complement. So here, right, we just write down the first number as is. But then we're gonna add it to the two's complement of this. Okay, so I take 0, 1, 0, 0. I flip it, 1, 0, 1, 1. I add 1, 0, 1, 0, 1, 1. Okay, so again, just to prove that when you take the two's complement of some two's complement binary number, that it negates it, let's convert these to base 10. What's 0, 1, 0, 0 in base 10? What's the sign of 0, 1, 0, 0? Positive. What's the magnitude? 4, right? Because when it's positive, again, you just find the magnitude like an unsigned. So you see this is +4 base 10. All right, we took the two's complement, 1, 1, 0, 0. What's this in base 10? Well, what sign is it? Negative. And then how do you get the magnitude of a negative two's complement number? What do you do to this? You flip it and add 1, right? Flip it, add 1. Lo and behold, see, it negated it. We had +4, took the two's complement, it made it -4. Okay, and then that's what we add. What we add to this, take the 1, 1, 0, 0. We get 1, 0, 0, carry the 1, 0, 1. Do that right. If I make a mistake, let me know. Okay, and then what do we say about this here? Is it valid? Yep, it's valid because we're adding a positive to a negative, so it's always valid. It's valid. Again, you just get rid of that 1 to the left, you assigned it. Okay. All right, one last one here. So again, we're going to have to take the two's complement of the second one. So tell me what to write here for the two's complement. This. Zero, 0, 1. Everybody agree? 0, 0, 1, 1. Flip it. 0, 0, 1, 0. Add 1. 0, 0, 1, 1. Add them. So 1, 0. Carry the 1, 0, 1. Not valid. Yeah, not valid, right? Because we're adding 2 positives. It comes out negative. So this is not valid. See, the reason why I'm spending more time on this, and right before we go over lab 4, is because, and I don't know if you noticed on Canvas, but I promised you last time, and I keep my promises. I delayed when lab 4 is due. Lab 4 is not due tomorrow. Like this labs is going to do the Wednesday after the Tuesday that give you all the information for the labs. I made lab 4 due after the midterm. Yeah, I think it's due Friday of next week. And the reason I did that is twofold. One, because lab 4 does take most students, I think, on average, more time than the previous labs. And also because the midterm's coming up, I don't want you to worry about the lab due right before, right after. So, it's due the Friday after. But I would not put off starting lab 4 until after the midterm. Like I would work on it. Some of you have already started because you started last time. I would try to do maybe get the modules working, and then maybe connect it all up after the midterm. And you don't want to wait, of course, until right before it's due to beginning, because chances are, if you do that, you're not gonna finish it. Okay, because there's definitely gonna be problems. You know, you should always anticipate anytime you do a design, that's not gonna work the first. But you know, lab 4, when you look at it, and again, we're gonna talk about it in detail, but when you look at it, it's not really that much more than what you've been doing. I mean, it's a bigger circuit, but as far as what you have to do, like new coding, it's not a whole lot. But the reason why it takes some students longer is because they're not used to two's complement. Okay, I've had cases where, you know, somebody will come up to me with their timing diagram for their overall, you know, after they've all put it together. And they're like, you know, Gary, this isn't working, you know, I put in this and I get that. And I look at it and it's like, that's what you're supposed to get. And a lot of times where the hurdle is just realizing that this circuit is interpreting everything as two's complement. And they're still thinking unsigned in some aspects. Okay, so anyway, that's why it's worth the time to do this review, I think. Okay, all right, let me move the camera. Now, do you have any questions before? Let's see. I'm gonna like go underneath here, unplug something. I'm gonna unplug this real quick. I'm not gonna like disturb your work. Yeah, there we go.
Didn't mean to trap you in there.
That's all right. All right, so let's come over here. Here. Actually, maybe I should. Oops. Sorry, my markers are fine. I guess. Oh, there we go. All right. That should be. Now, wait, in view yet. Huh. All right, that's good. Okay, so before I forget, just like all the labs, the test cases for the overall design are on Canvas. I think there was a few people I saw when I was just reviewing some of the lab scores from my student graders, that it seemed like there was a few students that still don't know about or forgot about that the test cases that you use, both for the simulation and the lab demo on the board, are in that Word file that's on Canvas. And make sure you use the test cases that are given, because if you use some other test cases, you're not going to get credit. And again, it should be both for the simulation and for what you test on the board. Okay. All right, so this is the diagram for lab 4. There's a hard copy of it on each table. That diagram's also on Canvas, but if you want to take a picture of it, okay, I only brought enough hard copies for the tables. I didn't bring enough for everybody because I gave you guys take a picture of it or look on Canvas. Now, before we do the high-level black box diagram for the overall circuit for lab 4, just a quick little review of these modules that are in lab 4 that you've already done. By now, you should all have an understanding of how an RCA works. Okay, in fact, that's one of the topics for the midterm. So what does the RCA do? Yeah, it just adds 2 4-bit binary numbers. Right now, you modified the RCA so it would have this additional carry-in input, right? Because you made it all full adders instead of 3 full adders and a half adder. So when you add that third input, that carry-in input, what's the RCA doing now? What is it going to do now? Just by adding a carry-in input. Without the carry-in input, it adds A and B. What is it gonna do if it has A and B and a carry-in? Yeah, just the RCA. I think you're thinking about more the, the entire circuit, okay? I'm just talking about this. You modified this to have all full adders, which, we added this carry-in because this carry-in of the RCA connects to the carry-in of that full adder that replaces the half adder. Right? So what's this RCA gonna do? And what does it do? Adds. That's it. It's just gonna add A and B and that single bit CN, right? So, once you have this modified, the way you test it is you use the same 10 test cases as lab 2, right? When you're testing out the RCA. And, set CN equal to 0. If you set CN to 0, you should get the same result as you got in lab 2, right? For those same 10 test cases. Then use another 10 test cases, the same as the previous 10, but then set CN equal to 1. And the result should just be what you had before plus 1. Okay, now I'll explain, and some people are kind of looking ahead, I think. I'll explain why we modified this because it has something to do with what you were talking about. Okay, but that's more the whole circuit, not just the RCA. Okay, so yeah, that's all an RCA does. It just adds the inputs that are on, it adds your inputs and then just puts that result as the sum along with the carry out. Now notice we're not using the carry out in this particular lab, and I'll explain. I'll explain the consequence of that in a little bit. Okay, how about a mux? Notice there's 3 muxes. 1, 2, 3. They're all the same type of muxes. They have 4-bit outputs and 4-bit or 2 4-bit inputs. How many bits does the select have to be if you only have 2 inputs? Just 1. So you see how each select is 1 bit. In fact, that's the mux that you designed earlier, right? So that's another file you can just bring over from a previous project. And this one you don't even have to modify. Okay. But how does a mux work again?
Decides what the output would be.
It decides what the output is going to be, and how does it do that?
So the mechanisms with it.
Right. The select input decides what the output's going to be, and specifically, how does it do it?
There's 2 vectors, well, it depends on how many inputs you want, but there's a certain amount of buses for the inputs, and then it just selects which bus next to it.
Exactly. So in this particular case, we only have 2 inputs. So if the select is a 0, what's going to happen? For this mux right here, if the select is a 0, what's going to happen? Right, the output is going to equal whatever's on the 0 input, right? So if the select is 0, this output would just be all 1. If the select is a 1, it's going to be what at the output? Yeah, 1, 1, 1, 0. And in fact, you remember what this mux in your lab 3 was doing? Because this mux in your lab was in lab 3 with the same input data.
It was just like.
Right, because the output of the mux is this AN, right? The anode of all the 7-segment displays. So when this mux was outputting all 1s, right, that would shut all the displays off, right? Because it would make all the anodes 1. Remember, it takes a 0 to light up a 7-segment display. And then when 1, 1, 1, 0 is at the output of the mux, that's when your furthest to the right 7-segment display would light up. So you see, this mux is doing the same thing as what the mux did in lab 3. What's different is in lab 3, the select was connected to the carry out of the RCA, right? Because our condition for lighting a segment was whether we had a carry out or not, right? Because that meant whether the result was 15 or less or more than 15. Here, notice that the select of this mux goes to the valid output. Okay, the valid output of your validity checker. So when you have a valid result, that's when we're going to show a result on the display. And when it's invalid, we're going to blank the displays. Okay. All right. So you know how an RCA works. You know how a mux works. All right. This decoder that we built. Okay. So here's the same decoder, the binary to hex decoder that you built in lab 3. So here's another module you just bring over from the other project, right? You don't even have to sim it, assuming that, you know, it was working in your previous project. So what was this decoder doing? It's right there in our names of our inputs. Right, and specifically, we made it so what would show up on the 7-segment display? Hex, yeah, exactly. That's why we call it a binary to hex, right? It's taking this binary, and how did we treat this binary, these bits at the input here? Did we know anything about sign at that point when you did lab 3? No, so how were we treating this binary here? If it wasn't signed, we were treating it unsigned, right? So the way you design this decoder, it was just taking the binary as unsigned and then converting it to hex by choosing the correct segments to light up. Okay? All right, so you know how all these work. Okay, now before we get into the details of this overall circuit, let's do the high-level black box diagram for this overall circuit, because what's the main thing you get? Actually, what's a keyword there? What's the main thing you get from a high-level black box diagram? What its purpose really is.
For the top level.
Right, the top level, and it gives us what of the top level? Yeah, the main inputs and outputs. So remember, this dash box, you know, what's inside, that's the details of, you know, what's inside this high level. What's outside the dash box, those are your main inputs and your main outputs. So how many main inputs do we have here? 3. You got A and B. Right, those are the two numbers we're either going to be adding or subtracting. Oops. One for the 8 there, one for 4. All right, so we got our 4-bit binary numbers like we did before, but now we have an additional single-bit sub input. This single-bit sub input, that's going to determine whether we're adding A and B or subtracting. Okay, and then how many outputs do we have for the high level? 3. We got seg and an just like before. Then we have this additional single bit output called neg. And what do you suppose that single bit output indicates?
If it's negative.
Whether it's negative, whether your result is negative. If it's negative, it's going to be a 1. So we'll connect it to an LED on the board. So when the LED lights, that means you have a negative result. And when you have a positive result, the LED will be off, right? Because it will be 0. Okay? So again, what's useful about a high-level black box diagram is this is giving your main input to main output. So, you know, when you create your structural model, you know, the top module that's making the connections, you're going to have to declare these inputs and these outputs for that module, right? Because that's the main inputs and outputs. Okay, so are you ready for how this circuit works? Any questions before I start looking at this in detail? Anything about anything we talked about so far that you have questions about? Ready? Okay, so when you're looking at a circuit like this, you kind of take it block by block. Okay. You know, here's our input side, here's our output side, and you know, the signals are going from input to output. Oh, I forgot to ask. How many people did like they were supposed to and watch the troubleshooting video that Dr. Benson made? Ah, very good. Oh, very good this quarter. Yeah, I asked my 8 to 11, it was the same thing. It was like 90% of the people. There was only a few people that didn't raise their hand. But that's really good. I've had quarters before where like 3 people raised their hand. Okay, so that's good. So yeah, the activity today, and I'll talk more about it coming up. But it's basically demoing that you can do what's shown in that video. Okay. All right, let's look at over here, the input side. We're just going to look at this mux with this inverter along with this first RCA. Now, like I said earlier, this sub input It's just a single bit. So on the board, it's just gonna be a switch. And when the switch is down and it's a 0, that's when we're gonna add. Okay, and when it's a 1, right, when the switch is up and it's a 1, that's when we're gonna subtract. Okay, so first, let's look at what happens when sub is 0. Okay, when sub is 0, it's gonna make the select of this mux a 0, and it's also gonna make the CN, the carry in to that RCA a 0. Okay, because this is all connected together, right? So, you know, if you had circuits, this is all the same node, right? 0 is like 0 volts, right? So as you know, a node has the same voltage, right? You don't have different voltage on the same node. All right, so what's the output of this mux gonna be if the select is a 0? It's gonna be B, right? Because when the select is a 0, whatever's connected to input 0, which is B in this case, that's what's gonna be at the output of the mux. And that output of the mux is connected right to the B input of the RCA. So what's the output of the RCA gonna be? Because what does the RCA do again? It just adds the 3 inputs, right? So it's gonna add A to B to CN 0. So the output of this RCA is gonna be A plus B, which is probably what you want when you're adding, right? When you're adding A and B, you want A plus B at the output of the RCA. Okay, so everybody good with that? So what happened to my other, I had a different mark. Oh, here it is. Looking for my green marker. All right, so now let's make this sub equal to 1. Okay, so that's gonna put a 1 on the select, and that's gonna put a 1 on the carry in of that RCA. So what's the output of the mux gonna be if the select is 1? Not B, because when the select is 1, it's going to connect the output to whatever's at the input of 1. And look, there's an inverter between B and the input of 1 of the mux. So right here, there's not B. And now that's what we're going to have at the output of the mux, which is going to put not B at the B input of the RCA. So now look what's happening. This RCA is taking A and adding it to B flipped plus 1. What happens when you flip and add 1 to a sign, two's complement number? It does what? You took the 2's complement, which does what to B? It makes it negative, it negates it, right? So you see, this inverter combined with adding to a 1, it's taking the 2's complement of B, which negates it, and now the output of your RCA is going to be A minus B. See, that's why we had you modify the RCA and make it all full adder. So we pick up this additional C in, so now we can flip and add 1 all in one step. See, notice that if you look at the internal signals that we have, you know, there's T1 here, T3, T4, T5, T6, T7. You know, there is no T2. Now, when you do this, you can name the internal signals whatever you want. All right, so if you want to put a T2 and not have a T7, or, you know, I would advise using more descriptive names like I've been, you know, saying all quarter. But you see, the reason why there's no T2 here is because at one time, instead of taking the 2's complement in one step like this by modifying the RCA, at one time, we took the 2's complement in 2 steps. Like we added A to the version of B with 1 RCA, and then we added 1. You know, that's what you would have to do if you had an RCA that had a half app. Okay, you basically would have to do this in 2 steps. Okay, but then we condensed it like you see now, and we didn't need this. Okay, so that's why there's not a T2. Okay. Usually if I don't mention that in class, I get all kinds of questions during class. They're like, where's T2? Where's T2? Okay, so is everybody good up to this point? Okay, because we got more to talk about, but does everybody see that when the sub input is 0, we're going to get A plus B. When the sub input is 1, we're going to get A minus B at the output of that first RCA. Everybody good? All right. Well, we already talked about what's going on here with this mux, right? Because again, this mux is controlling whether the furthest to the right segment's gonna light or whether nothing's gonna light based on the valid output, right? So everybody agree with that. I usually don't spend much time here because this is just like lab 3. Okay, the only difference is we're using valid for the select instead of the carry out. Okay, but I did talk about this last time, but I just want to make sure, that it makes sense to everybody. That the 3 inputs here to the validity checker, notice that they're going to the 3rd bit. This input's going to the 3rd bit of A, right, which is one of the binary numbers we're adding or subtracting. T13, that's the 3rd bit of what's coming out of this mux, which is either going to be B or not. Right, and then this input here is going to the 3rd bit of T3, which is the same as the 3rd bit of the sum, which is the result. So why is it the 3rd bit that we're interested in when we're trying to determine validity? That's the sign bit, right? And that's what validity depends on, right? So you see, that's why we're taking the sign bits of what we're adding along with the sign bit of what the result is, right? Because that's what you need to test those rules. Okay, so does that make sense? All right, let's look at this AND gate. The output of the AND gate, it goes to this neg output, which again, like we said earlier, it's going to light when the result is negative. It's not going to light if the result is positive. It also goes to this select of this mux that we'll get to later. But right now, what is it going to take on the input of this AND gate in order to light up this neg LED, this neg output? We need a 1 here, right? To light this. So what do the inputs to my AND gate have to be to get a 1 out?
Well, sign and whether it's valid.
Right, both of these have to be 1, right? Remember an AND gate, in order to get a 1 out, all your inputs have to be 1. So this 1 would mean it's valid. This 1 would mean it's negative, right? Because that's telling you the most significant bit of the result is negative. So if the result is negative and valid, that's when we're going to light up the negative. And also put a 1 on this select. And again, I'll come back to why there's a 1 on that select. Okay. If the result is positive, right, this would be a 0. And remember how we talked about it only takes 1 0 at the input of an AND gate to get a 0 out. So, if you have a positive, valid result, it's not going to light up the neg, right, which you don't want, right? It's positive. Also, if it's negative but not valid, they were also not going to light it up. Okay, and then also, if it was not valid and positive, we wouldn't light it up. Right? We're only going to light it up if it's negative and valid. Does that make sense? Okay, so let's say, before I do the next thing, I just want to emphasize again that this decoder that you already built, when you designed it, it was designed to treat this input as unsigned. Okay, and again, it's taking that unsigned and showing the hex character. Okay, all right, well, let's talk about why we have this, why we have the second RCA along with this second mux. So first, let's say that the result is positive, right? So that's a 0. And, let's say it's a valid positive result. Well, that would make the output of this and a 0, which is going to shut off the neg output like we want. It's also going to put a 0 on this select. Okay, so if there's a 0 on this select, what's the output of this mux going to be? Right, it's just going to be the output of RCA1. Right? So we would have A plus B here, or it could be A minus B also, right? But the key point is it's going to be the output of that first RCA that's going to be on this 0 input. And then with this select equal to 0, it's going to put that sum output right here going into your binary to hex decoder. Well, if we have a positive result, how do you find the magnitude of a positive result? We talked about it earlier. It's just like unsigned. Right? So you see, your decoder here is going to work fine the way it is if the result is positive. Okay, does that make sense? Because that's how you designed it, right? Well, you didn't design it for a positive number because you didn't know signed numbers at the time. You did it for unsigned, but positive signed is just like unsigned. So you kind of think of that you did it without really realizing it, right? Okay, but what if this is the situation? Okay, let's say we have a valid negative. Okay, and for example, let's say the negative result is 1010. So, the result of either our addition or subtraction comes out 1010. So what is this in base 10? And remember, we're treating this as 2's complement, right? So what is 1010 in base 10? Negative 6. Right? Everybody agree? Right? This sign bit tells me it's negative. That's an S. There's supposed to be an S. Right? The sign bit being 1 tells me it's negative. And then to get the magnitude, I flip the bit. So 101, I add 1. Right? So negative 6. But what if we put 101? What if we were to put 101 into your decoder? Would it display 6? No, what would it display? Because how did you design it if there was a 101? A, right? Because that's 10, and A is 10 in hex, right? So if we had connected the sum output of this RCA directly to the decoder, when you had a negative result, it would not show the right answer on the 7-segment display because you didn't design it for negative signed numbers, right? You designed it for unsigned, right? Shown as hex. So you see, that's why we have this additional circuitry, because if we have a negative number as a result, what's this inverter going to do? What does an inverter do? It flips it. Look, Cin is connected to 1. So this RCA, it's going to flip A, add 1. Now there's the other input here, we made 0, which isn't going to have any effect. But if you flip the bits of something and add 1, what are you doing? Said earlier, you're taking the 2's complement, so it's going to negate it. So we're going to have a 6 at the output of this RCA, and we're going to select that, right? Because the output of this AND gate is going to be a 1 if it's negative and valid. So now instead of having 1010, which would display an A based on how you design the decoder, it's going to display a 6. Right? So you see the reason why this second RCA along with this inverter, like this whole circuit right here, the reason why it's here is because you designed this to take unsigned to hex. All right, but now we're dealing with signed. And that becomes a problem when it's a negative number. It's not a problem when it's a positive number, right? Because like we said, you treat positive 2's complement magnitude just like unsigned. Okay? Another way this lab could have been done is that we could have, instead of having this, having this circuitry here, we could have just had you design another decoder where you treated the input as a signed 2's complement, right? And then base the output off of that. It'd be a different truth table. It'd be a different case statement. Okay. But the reason why I like this, now I'm not the person that designed this. I think it was Dr. Benson or Dr. Mealy. But the reason why this is, in my opinion, a really good design, a really great lab for people, learning not only digital, but just engineering. This is typically what happens in engineering. Like practicing engineers, you have something already that is good. You have something else that is really good, but they won't work together. So you got to interface it somehow. So this circuitry here is interfacing 2 things you had previously. Now, you have to modify this some too, and that's also what practicing engineers, mostly do. Unless you're working like an R&D, state-of-the-art type job, usually don't start from scratch. Like you start with something that you can get fairly easily, like what we call off the shelf. And a lot of times off the shelf doesn't quite meet what you want it to do. So you have to modify it in some way. And then you might have two things that don't work together directly, and you got to put something in between that, you know, makes them work together. Okay, so I really like this lab because, like I said, it's really a good example of what practicing engineering is all about. Okay, so do you have any questions up to this point? Now, the reason why, or a reason why, I made the activity, you know, watching that Dr. Benson troubleshooting video and then you showing me that you can do that technique is because once you get to circuitry like this that has a number of different modules, the probability that this circuit is going to fail the first time you try with everything connected is pretty high. And also, like when you get the circuitry like this, a lot of times you'll test the individual modules and they'll be fine. Like they're giving you the timing diagram they're supposed to, and the individual modules by themselves are great. But then when you connect it all up, it doesn't work for some reason. And a lot of times, you know, you go to look at the elaborated design schematic, because that's a good way to check if your top module is right? Because, you know, a lot of times you'll look at the schematic and it won't look the same. There might be a connection missing, or maybe a module's missing, or something. But there's other times where you look at the schematic and it also looks good, but yet it's not working overall. And that's where using Dr. Benson's technique really is helpful, because by being able to pull out intermediate signals and putting it on the timing diagram, you can follow the signal through. You know, like say it's not working for A minus B, but it's working for A plus B. First thing I would do is look at this output for an A minus B example and see if it's what it's supposed to be. If it is, well, that means everything to the left is working the way it should. The problem is further down. You know, if it's displaying a hex character, right? For any test case, if it's showing a hex character, there's probably something wrong right here. You know? So, you know, you'll find, especially by the end of this class, and also definitely when you take CP233, that technique that Dr. Benson shows you is invaluable. Sometimes it's really the only way to narrow down where the problem is. Otherwise, you're just troubleshooting in the dark. Okay, so that's why, you know, I made it an activity, and that's why I want each student to show me that they know how to do it, because it's just so important. Okay, all right, so any questions? Now, it's the top of the hour, but it's probably only going to take me another like 10 minutes or so to finish. So I think I'll just continue here, unless there's a big objection. Does anyone object strenuously? Okay. So anyway, this is a suggested order for lab 4. You know, modify your RCA and test it. Remember, we talked about last time, you should have 20 test cases for testing the modified RCA, because you got to do the same 10 as you did before with Cn equal to 0, right? So you have 10 with Cn equal to 0, and then the same 10 again with Cn equal to 1. Okay, that will thoroughly test it. And please thoroughly test this, because I can't tell you how many times, you know, somebody has, you know, an overall design that doesn't work, and they've checked all the modules except for the RCA, because they're like, oh, well, it's an easy mod. It worked in lab 2, so I'm sure it's working now. And then it turns out it's not working. Okay, so make sure you test it. You know, create the validity checker and test it out. How many test cases should you have for the validity checker, whether you do an if statement or whether you do a table? The same amount, either way. 8, right? There's 8 different combinations. So you should do 8 for the validity checker. Okay, so once you have those modules all simulating correctly, you know, bring over the MUX from one of the previous, well, lab 3, bring over the decoder from lab 3 again. You don't have to retest those as long as you simulated it in lab 3 and it's working. Now you're going to do the top module. Okay, I call it add subtract. You can call it whatever you want. So now you got to make the connections. Okay. Now there's a few things here you haven't seen before when you go to make the connections. Now this one you have seen before, right? You had to do this in lab 3. You had to connect the input of a mux to some data. So how did you do that? Like, how did you connect input 0 to all the ones? What was the code that you needed? Don't remember, you did this. You had to have done it for lab 3 to work. So what would we do? What do I write here? I want to connect input 0 to all those ones. Nobody wants to talk today. So that's what I always think. Sometimes teaching is like practice for being a dentist because you always got to like pull teeth, get answers. You just don't want to tell them. Somebody tell them. Well, yeah, we're doing the code for the top level, but I'm specifically asking like what syntax, what code would you write? I want to connect this 0 input to that data.
Like our connection where we
Yeah.
have the name of the variable and the value.
Yeah. So what would you tell me what to write?
So MU
Well, we don't have to do the whole thing, just like the specific code that makes that one connection. Yeah, you got to put the line like the file name. Maybe that's why people were hesitant. They didn't know exactly what I want. I don't want the whole line. I just want, specifically how you make that connection. So it'd be what?
Okay, so input 0 and then in parentheses the 4 bits 1.
Right, there's one thing. Oops. There's one thing we need before the 0.
It's a period.
Yeah, the dot. Oh, and I got confirmation from a student in my earlier section today that you can actually use numbers as input names. Like he said, he did a .0 and it worked. Remember, I wasn't sure about that. I think at one time, because when I originally did this was many versions ago. It was probably like version 2015 because it was like 8 years ago or whatever. And maybe back in that version you couldn't use numbers as input names, but maybe the new version, because he told me he was using 2023. So anyway, it appears that you can do that. But yeah, you've done that. So you do the same thing here. All right, but you haven't seen this. You haven't seen how to model inverters in a top module like this. Well, the way you would do that, and specifically looking, say, at this inverter right here. So again, it would be in the line for that mux. But the specific code to model the inverter is you would just go it's .1, and then in parentheses, you would just put tilde and then B. And if you were just connecting it to B, there'd be no tilde. But if you want it to be not B, okay, you put the tilde. It's just like in a Boolean expression, the tilde is the not, same thing here. So you see that tilde, that's taking care of that inverter.
What's the .1 from?
The .1 is because I called this input 1.
Oh, okay.
Yeah, that's all. Okay, now to do the AND gate. Again, in the top module, this is all in the top module, what we're talking about here. To do the AND gate, you use an assign statement. All right, so it'd just be assign T6, right? Because the output of this AND gate is this internal signal T6. And then you would just set it equal to, T3, the third bit, ANDed with valid. In that assign statement, it can either go above where you're making the connections or below where you're making the connections. Okay, I don't think you can, well, I'm positive you can't put it between where you declare the inputs and where you declare the internal signals. It's going to come after the internal signals. Okay, and then for neg, you would just use another assign. You would just assign neg the T6. Right, to see how the output of the AND gate, the select input, and also the neg output, they're all connected to this T6. Okay, so with that, you should be able to complete lab 4. Now, again, you've got extra time, it's not due till Friday next week, but like I said previously, I would start, not wait until after the midterm to start it. Now, the last thing here. Okay, last thing Today's activity is you just need to show me or the ISA. Kathy may get here early. I don't know. But whenever she gets here, you can show her too. So either myself or Kathy, just show that you can drag the signal over to the timing diagram and then also show that you can run it for 120 nanoseconds. The reason I picked 120 nanoseconds is because if you look back at lab 3 had more than 10 test cases. It had what, like 16 test cases? So make this, instead of 180, make this, or 120, make it 180. Okay, the reason I chose this time is because in your sim file, you know how you put the number sign 10? Right, you put number sign 10 test case, number sign 10 test case. Does everyone understand what that represents? I talked about it in my intro video. What does this mean, number sign 10? Yeah, 10 nanoseconds. So we're putting 10 nanoseconds in between each test case, right? If you didn't have that, like if you just listed the test cases, they would all be on top of each other. And you would just see gibberish, okay? So if you have 16 test cases, that's like 160 nanoseconds to do the entire amount of test cases. So if you run it for 180, that would be like just enough time. Yeah, maybe just a little bit more. So that way you're just showing the test cases one time instead of it repeating. Okay. You know, another thing I noticed when I was looking through some of the grading for the labs is, now this isn't a lot of people, but there's a number of people that when they're turning in screenshots of timing diagrams, the timing diagrams are nonsensical where, you know, you have green waveforms, but you can't see what the data is. Like the grader can't see, you know, that for, you know, 0 plus 0 is 0 and 0 plus 1 is 1. It's just like, you know, it's not expanded enough. So it's showing like just little dots. Okay. You know, if you pass in screenshots of simulations that don't verify that your design works, it doesn't get credit. All right. I mean, as I said before, you know, you definitely don't want red and blue waveforms because that means something's really wrong. But you can still have all green waveforms and it not be right. Like the data could be incorrect. Okay, so make sure what you turn in is showing that the design works. Now, what I hope happened is that the person had it at one time correct, and maybe they just made a mistake before they submitted it. But you know, you got to take responsibility for what you turn in. Okay, make sure things are right when you turn it in. Just don't turn in something. Okay. All right. So the last thing here actually is I just want to point out some things on the handout. There's a handout everybody should have about my policy for midterms and also the topics. Again, this is on Canvas. And you know, I may do things differently than other instructors, but this is what I do, for example. So during any type of exam, I don't provide any help or assistance. You know, before an exam, after exam, I'm more than happy to help give you answers, but during an exam, that's an evaluation. Okay, so I don't help, I don't give answers. If you have a question during an exam, any type of question, write it on the exam. Okay, don't come up and tell me verbally, because if you do, I'm just going to say, write it down. Whatever you write down, I'll consider when I do the grading. If you tell me something, I'm not going to remember it when I grade. Okay, so, you know, like, for example, if you think there's a typo, just write, you know, I think this is a typo. If you meant this, this is what I would do. All right, I don't purposely put typos. Okay, but if that happens, that's what you would do. Also, this is very important because I don't care if this is inadvertent or not. If you have a phone on your desk while you have possession of the exam, that's an automatic failure. I don't care if you're on your phone. It can just be laying there. Okay, so what you should do for any time you take an exam with me is put your phone away right away. Put it in your backpack, in your pocket. It just can't be on the desk. Okay. You can leave the room during the exam, but if you do, you have to leave your phone with me. And only one person can be out of the room at any given time. So if you leave the room, make sure you come back as quickly as you can because there might be someone else that wants to leave. Okay, and you can use calculators, but you have to show your work manually. I grade on work shown. I don't grade on the answer. So, and I don't care how simple it is. Like, say you have something like this on the exam, you got to show me manually that you can do it. You got to show the carries if there's a carry, and just like what I've been doing in class. Okay. Most of the time, what happens if someone doesn't get the exact work and the answer I have, like typically the most common thing that happens is, somebody will have an answer that's different than mine, but when I look at the work, I see that they just made like a minor error, and they'll either get full credit or, almost full credit. For example, sometimes on a test, you'll have people, they add, like 5 and 2 and they get 8 or something, I just attribute that to stress on a test. Now, what sometimes happens, but it doesn't happen a lot, but it has happened, is somebody will have the same answer as mine, and I look at the work they've provided, and in no way does that work lead to that answer. There's just like no way, unless they left a bunch of stuff out. Okay, and in a case like that, the person gets no credit or very little credit. Okay, so I grade on work shown. I do not grade on the answer. In fact, sometimes I don't even look at the answer. I just look at the work that the student provided. Okay. Okay, and then for the topics, notice I put list may not be all inclusive. That's just there just to cover myself if there's something I missed, but I think I was pretty thorough with the topics here. I would go back, when you prepare for this, I would go back and look at the activities. Also, look at your notes. Now, if you're a person that doesn't take notes, maybe you want to go back and look at my recordings, okay, especially if there's something you're not sure about. Like I would go through these topics and I would check them off as I, make sure I'm prepared for them. Number bases and number base conversion, that goes way back to the beginning of the quarter. That was the first day of class. BCD, remember we talked about that. That's a way to represent a base 10 number as 4-bit binary groups. A bunch of sign stuff. We've been doing that the last couple of classes. Digital forms, go back, make sure you understand SOP, POS, NAND, NOR. Remember how we converted between the two, right? There's activities on that. Universal gates, what are the universal gates? NAND and NOR, remember you can make all the other gates out of those, right? K-maps. Now with K-maps, I will give you the cell numbers and I will give you like where the rows are for A and B and so on. Now structural modeling, that has to do with like not writing, like I won't ask you to write code, but I could give you code that I want you to interpret. Or, I could give you a diagram, or I could ask you to draw a diagram, right? You had an activity on those types of things. You should know how these different modules work, right? We even reviewed today the RCA, the MUX, the decoder. You should know how a comparator works. Now, a comparator wasn't part of a lab, but I did use it as an example of an if statement. And how it works is right in the name, right? Comparator, it's comparing two inputs, and it determines whether it's greater than, less than, or equal to. Okay, it's likely you'll use a comparator for your final project. A lot of times people find they need comparators for that. Timing diagrams. Okay, so this is probably, of all the topics, this topic has the most to do with, I think, with the lab, right? Because I think I had one activity on a timing diagram with MUXes, but this is here mainly to see if people are understanding when they do a lab and they have to verify their design that they understand a timing diagram. Okay, so if you're shaky on that topic, I would go back and review some of the labs that you've done and make sure that you understand, like, okay, how to look at these are the inputs and what output I should get. And, timing diagrams just show your inputs and outputs as time progresses, right? Let's see, what else here? Do you have any questions about anything, any concern? I mean, like I said earlier in the quarter, I think someone, now, again, I can't give any guarantees, okay? But I think someone who has been attending class that has conscientiously done the activities, meaning that you're actually doing it yourself, you're not like relying on somebody. And you understand, right? That's the most important thing, because that's what exams test for, is that you understand. What we've been going over. I've been doing the labs conscientiously, like you're actually the person doing the lab and it's not someone else doing it for you. And again, the key thing is that you've been understanding what we've been talking about through the quarter. Then I would think a person like that would do well. Now, again, I can't give any guarantees, but that's what I would think. Because when I make an exam, my intent is that for a person that understands the material, they should do well. A person who doesn't understand the material should not do well. I mean, that's what an exam is all about. Okay, so I mean, any questions or anything on this? No questions? Boy, you're very quiet. You're one of the quietest sections I've ever had. So that's either a good sign or a bad sign. I guess we'll find out. But hopefully it's a good sign. Hopefully things are making sense. So, okay, so for the remainder of today's class, you definitely want to show me that you can do that. So you get checked off. That's today's activity. And then after that, work on lab 4. If you want to go somewhere else and work on lab 4, that's fine. But before you leave, make sure you show me that demo. Okay?